So now that we've worked our way through a lot of organic chemistry, you've had a chance to see some different functional groups. And what I wanted to do is, first of all, introduce you to a new functional group and then one of the molecules that contains it. But I think the best way to understand this functional group is to take a look back at some of the previous functional groups that we've seen before. So we've seen two functional groups in different molecules. So one was a hydroxyl functional group where you had an OH attached to a carbon. You also had a carbonyl or carbonyl functional group that has a carbon double bonded to an oxygen. And the new functional group that I want to introduce today is called the carboxyl, which is actually just kind of like a mashup between the hydroxyl and the carbonyl. So what you have is your carbon double bonded to the oxygen, just like from the carbonyl carbon. And then you have a carbon attached to an oxygen with a single bond, and that is all connected to the same carbon. This is what we call the carboxyl functional group. And what's connected after this oxygen depends on what that molecule actually is. A carboxyl functional group is something that we see in a couple of different molecules, but what's important to understand about it is you have a carbon using up 3 of its bonds to attach to a couple oxygen atoms. So you have that double bond going to one oxygen and a single bond going to another. And what that means is that carbon only has a single bond left. So that means that a carboxyl functional group is never going to be inside of a ring or inside of a ring structure based on what we're going to see. And it's always going to be at the beginning of a chain when we look at it. Now, what I wanted to introduce first was one of the molecules that we end up seeing this in, and it's something called a carboxylic acid. So when we're dealing with a carboxylic acid, what we're really dealing with is a structure that looks like this. You notice if we kind of cut out the H, we have that carboxyl functional group. We have a carbon double bonded to an oxygen, single bonded to an oxygen, and that oxygen is then connected to a hydrogen. This creates a carboxylic acid, and when we name a carboxylic acid, we name it using the ending OIC acid. So in other words, we're going to call it oic acid. Because this is an acid, it actually functions the same way most acids do. It is able to taste sour. It is going to have a lot of those other properties that we talked about. It's going to turn litmus red and all that stuff. And as an acid, it's actually going to end up donating this hydrogen during chemical reactions. And so that's why it is actually an acid. Now, what I'd like to do is work through some examples, and I'm going to introduce you to one of the most common examples that we end up seeing related to carboxylic acids. So this is one example of a carboxylic acid. You might know this better as CH3COOH, and up to this point we've been calling this acetic acid, which is a common name that's used. But if we wanted to look at the proper naming of this, what we want to do is find our longest chain of carbons that still contains that carboxyl functional group. So we have a 2-carbon chain. So I'm going to add ETH, F, as the beginning. I'm going to write AN next because there is only that single bond connecting them. Then, to show that I have this carboxyl functional group as a carboxylic acid, I add oic acid to the end of the name. And because it's always at the beginning or end, depending on how you look at it, of the chain, because it's always at the beginning of a chain, it would always get the number 1, and so we never have to write the number 1. Very similar to an aldehyde. So this is called ethanoic acid, better known as acetic acid. One of the really common questions you get early on in chemistry is, why is acetic acid written CH3COOH? And why is it that the H is the thing that reacts? Well, the reason why is because it's a carboxylic acid. We're actually writing out the formula in the same manner that you would write out an organic formula. That H at the end is the thing that tends to leave in reactions and not the H is connected to the C, because these are bound tightly by a carbon-hydrogen bond, whereas this hydrogen is able to leave more freely as an acidic hydrogen and be donated. So this is an example of how we would name a carboxylic acid. And now that we have this down, let's take a look at a few more examples that might be a little bit more challenging. So we're going to start with this. We're going to start with propanoic acid. So if you're reading through this, you should read through and say, okay, prop, 3 carbons, single bonds between carbons, oic acid, that should tell you carboxylic acid. So you know you have that carboxyl functional group. So what that means is I'm going to have my 3 carbons connected to each other. I have a carboxylic acid on one side. Now, it doesn't really matter which side you draw it on. You can draw it on whichever side you like. And then I have these other carbons that have to be filled out with bonds. So I'm going to have CH3 on the end and CH2 in the middle. And there we go, propanoic acid. So that's how we go from the name to the formula. So now let's try one where we go from the formula to the name. So in this example, you can see we have our carboxyl functional group. I know immediately this is going to be a carboxylic acid because I have a carbon double bonded to an oxygen, single bonded to an OH group. So immediately I'm going to know carboxylic acid. So what I want to do is find my longest chain of carbons that contains this group. So 1, 2, 3, and 4. That means I'm going to use bute as the main parent chain's name. I also only have single bonds connecting all of those carbons. So I'm going to go AN, so butane, oic acid to represent that it has that carboxylic acid group. And now we need to talk about the substituent that's on the side. So we don't give a number to the carboxylic acid in the name because it's always going to be number 1, but we still use that system to number our substituents. So what that means is I have a 1 carbon branch here. So I have a methyl group in the 2 position. So 2-methylbutanoic acid is how we would end up naming this. Okay, so now that we've seen that, let's try another one. Okay, so here we're given another molecule. You can again immediately tell carboxylic acid, carbon double bonded to O, single bonded to OH. Don't be fooled if it's changed direction or something like that. It just means that the molecule is oriented a little bit differently. So we have our carboxylic acid, this would be carbon number 1, 2, 3, and 4. So it's still going to be some kind of butanoic acid. And we know that because single bonds only for the AN, carboxylic acid group for the oic acid ending. And now we would want a number. So we would go carbon number 1 because of the carboxylic acid group, then 2, 3, and 4. So this is 3-methyl butanoic acid. So just pretty much really similar to what we saw last time, moving that methyl group from the 2 to the 3, but you can see it's kind of been like flipped. It's almost like a mirror image vertically from what we saw last time, except for the placement of that methyl group. Okay, so now that we've done this, let's mix this with another functional group. So we're dealing with another carboxylic acid in this example, but we have our carbon double bonded to our oxygen, single bonded to our OH group, so carboxylic acid, and then on the second carbon, you notice there's something totally different here. So we have a fluorine that is in this molecule, and we're going to have to account for that in the name. Now, when it comes to the name, we're still going to do it the same so that we count the carbon, that is our carboxylic acid carbon, and then we count our longest chain of carbons that contain that. So 1, 2, 3, 4. Again, butanoic acid. Butanoic acid because 4-carbon chain, single bonds between carbons, carboxylic acid group at the beginning of the chain. Now we next need to name this part. So remember, with these, we are going to use prefixes, and to show the prefix for fluorine, we write fluoro. So we have fluorobutanoic acid, but we now need to know what position it's in. And the carboxylic acid is a priority group, changes the molecule more than anything else in it. So 1, 2, 3, 4. You always have to start at one end of the chain, and since the carboxylic acid group is there, it gets the lowest number. That makes the fluorine in the 2 position. So we get 2-fluorobutanoic acid. So this is how we deal with mixing alkyls and halogens into carboxylic acids. Now, I will state, I won't be mixing any carboxylic acids with anything outside of alkenes and fluorines, because as soon as you do, you end up changing the naming system quite significantly. And so at a high school level, this is basically as complex as we tend to get. That being said, it is more than possible to have a carboxylic acid with an alcohol or a ketone or an aldehyde even on the other end of the chain. And so you end up having different naming systems to represent all of these different possibilities, but we're just kind of like wading into the waters of organic naming. And so this is basically as complicated as it's going to get. So this is one example of how we end up seeing a carboxyl functional group is in the carboxylic acid. And up next in my next video, you can check out how we would name something called an ester. So thanks for watching, and I'll see you next time.